Mm. All right. Um, what we'll do today? So today we'll discuss 130 nanometer CMOS process flow. Uh, so here we'll see how to fabricate NMOS and PMOS transistors. So basically, when I talk about CMOS, so CMOS here is nothing but NMOS plus PMOS, right? NMOS transistors plus PMOS transistors. So we discussed in the class, we discussed about N-type MOS transistor and P-type MOS transistor. So we'll see in means how to fabricate those transistors. And I have chosen 130 nanometer CMOS process flow because this is this is standard process flow for analog and RF devices nowadays. Um, okay, so so let's go to the next. So if you look at a typical VLSI circuit, right? So let's say I don't know how many of you have seen an integrated circuit. So if you take an integrated circuit, right, and take a cross section of the integrated circuit, right. So if you take a cross section of an integrated circuit, so you will see something like this, right. So you'll see something like this, right. So here, um, your transistor, so you will have your transistor. So if it's a CMOS technology, so you'll have you'll have NMOS and PMOS transistors as active devices, and also you'll see a layer of back means layer of metal lines, right. So since this is a 130 nanometer CMOS process flow, so generally 130 nanometer CMOS process flow is so we have 6 to 7 metal lines, and here we have so this cross section only shows up to metal 6, right. So so in this cross section your transistor sits down, right. So this part is your transistor here, right. Your transistor is somewhere here. So this is a NMOS. You don't know from the cross section. You cannot really know whether this is a NMOS transistor or PMOS transistor. But if you zoom the transistor part, you will see the structure that is in the right hand side. So you'll have gate. So here the gate is made of polysilicon, right. So the gate is made of polysilicon, and you have a thin oxide layer. You could see this oxide layer is somewhere here. So you have a monocrystalline silicon, then you have polycrystalline silicon gate, and your gate oxide is somewhere here, right. So you could see there is the gate oxide, right. And then even so these regions is your spacer region. So because this, so basically spacer is needed. So if you means we'll look at the MOS transistor structure. So basically if I go to the transistor schematic, so this is generally the transistor schematic. So your NMOS transistor, so basically this is a two in well process, right. So we have two wells. So we have P type substrate, and we have two wells, P well and N well, right. So your NMOS transistor is in P well, and your PMOS transistor is in the N well, right. So basically for NMOS transistor, if you look at the substrate is P type, so this is a P well, and for a PMOS transistor, substrate is N type. And your transistors are separated by isolation. So these are called shallow trench isolations. So shallow trench isolation is also used in bipolar technology. So you have shallow trench isolation. So here, if you look at the source and drain of your transistor, right? So typically, we discussed that okay, source is N-type and drain is N-type, but actually, to avoid short channel effects, right, which we have not discussed till today. So to avoid short channel effects, so if you look at the source and drain, so these are two parts, right. So one part is your extension part, right. So this part is called extension, right. So this is the source and extension. This is a the thickness of the extension region, right. So this is my extension region. The thickness of the extension region is smaller than the main source drain region, right. So the other region is your main source drain region. This is your main source drain region, and the other one is your extension part, right. So you have this extension. We'll come to that point later when you discuss about short channel effects. To avoid short channel effects, right. So the extension and the source drain is separated by something called spacer. So this is my spacer here. Uh, so these are spaces your source drain and main source drain extension separately, right? And similarly, also in the P type, we have PMOS transistor. We have also extension and source drain region, and we have also spacer, right? And this is my contact plug, right? So this is the contact, this is my contact, right? And because so my transistor, then transistor, it's basically uh, your transistor, the current will go, means basically to the metal line. So basically this is the metal lines and your transistor is connected by something called contact, right? So this black region here, these are the contact region, right? This is the contact. So if I go back to this typical cross section of an integrated circuit, so basically this part, right, where we fabricate the transistor, this is called the front end of line processes, FUL. So you'll study about it in more detail when you do the microfabrication course. So this is called front end of line process. So this metal and the vias, these are called back end of line process. Back end of line process. This is back end of line process. So back end of line process starts from metal one, right? So from metal one, all the metals. So this is the back end of line process. Your front end of line process starts from the silicon wafer, then till the transistor is fabricated. So you have silicided, right? Your source drain is done and annealing is done, right? And in between this contact part, right? So this is called mid of line process, right? So the contact is something different, right? So the contact, right, it connects your front end of line to back end of line part, right? So this is called the mid of line, right? So typically if you go to a fab and work in a fab, people will talk, okay, mid of line process, back end of line process, and front end of line process, right? So if you go to a typical fab also, the back end part in done in a separate room, front end part done in a separate room, and mid of line is mostly done, it could be done with front end of line process, right? So because the back end of line process is mostly metals are involved, right? Aluminum or copper, right? So in advanced technology, we have coppers in the back end. So we don't want your semiconductors to be contaminated by the copper, right? So we have already studied in this course, right? So if you have, let's say you have a semiconductor and let's say it is contaminated with copper, so then the copper will create a mid gap state, right? So that means the semiconductor will not be pure, right? So it will have defect states, which is rightly sitting at the mid gap, and it will have issues, right, in the recombination and the enrichment process. All right. So okay. So basically, when you look at the layout, right? So when you look at the layout, so your layout looks like this. So this is your NMOS transistor, and this is your PMOS part. So NMOS and PMOS. So if you look at the NMOS, so you have active, right? So you have active and gate, right? So the shaded part is your gate, right? So this part is your gate, right? This is the polysilicon gate, and on the other part, this part is your active, right? So this is your active, and you draw it like this, right? And these are the contacts, right? So these are the contacts that you have drawn, right? So when you talk about width and length of the transistor, so you know, right? So width is the width of the active region, that is your width. Length is the length of the gate part, right? And the active, if you want to have the area of the transistor is W times Lg, and similarly for the PMOS. But keep in mind, the PMOS is in the N well, so this red line is drawn is N well line, right? And the NMOS is in the P well, right? Okay. So when you means for the fabrication, before fabrication, we have to draw our layout. So you draw the layout by defining different layers. So these layers are nothing but the polygons drawn during the layout to define a device. So these are the layers, right? And the masks are derived. So you have drawn some layers, right? Then the masks are derived from these layers, right? And the number of masks may be more than the number of layers, right? So layers is what you have drawn during the layout, and the masks So once you send your tape out, once you send your layout to the fab for fabrication, the fab will look at the layers. Then based on the layers, they will generate masks. So the number of masks may be more than the number of layers, right? So masks are typically used for fabrication. We'll see how. Right? So when you talk about layers, means many of you might have done the layout. Typically we draw these layers in a simple CMOS flow. These layers are like active layer. So you draw the active. So this is the active area of your device. Active, NOL. So these are the layers that are typically drawn, right? Active, NOL, gate, NSD, N source drain, P source drain, contact, metal 1, via 1, metal 2, VR2, metal 3, VR3, metal 4, VR4, like that, right? So these are the layers that you draw. When you do a layout, you draw these layers, right? Then your fab will look at these layers, then they prepare masks based on some algorithm, right? So they call it Boolean. So they have some algorithm. So they will read your layer and accordingly they will prepare the masks, right? Okay. Um, the starting material, right? So starting material, when you do mass transfer fabrication, is silicon wafer, right? So silicon wafer, we generally use P-type silicon wafer. So we use P-type silicon wafer with different resistivity, right? To start with. So when you talk about wafer, right? So the wafers are so basically typically the fabs, right? Fabrication houses or the the fabs, they do not actually invest so much in the wafer growth, right? Wafer preparation, right? So basically the wafers are manufactured by separate companies. So this fabrication facility, they just buy the wafers from these wafer vendors, right? So the wafers are generally made means the by the technical crystal growth, right? So the crystal growth. So basically, you take the silica, then you melt it, then you pull the crystal, right? So crystal growth. So you'll know about it in more detail when you do the fabrication course. So if you look at this, right? So here this part, right? So this is how you are pulling the crystal. So what you do is you take the silica, right? Means that is available in the earth, and then you melt it, right? And then you slowly pull it, right? So when you pull it, so this is called the ingot, right? So you'll have the pure silicon ingot, right? And you have to slowly pull it, right? So it will like a cylindrical thing. So this process. So this is my crystal ingot, right? By silicon ingot. So then you have this ingot here, right? So once you have this crystal growth, right? So this is the crystal growing process, right? So we have different growth techniques like Chokralski growth or floating zone. So there are different growth techniques. So the growth will give you something like this, right? So it will give you a silicon ingot, right? So it's cylindrical, right? And the diameter, right? So diameter of this is fixed, right? So diameter of this silicon crystal or silicon ingot is depends on how fast you are pulling, right? So if your crystal pulling process, so basically if you pull the crystal slowly, right, from the melt, right, very slowly, then it will be I mean diameter will be large. If you pull it fast, then the diameter will be small, right? So this is how you control the diameter of the ingot, right? So then you take that ingot, then it goes through several processes like sawing, profiling, lapping, grinding, etching, polishing, then inspection, then cleaning, then you package it, right? So basically, you have the ingot, right? So you have to cut it, right? So you have to cut it. So this is called sawing, right? You saw it, right? When you cut it, your surface will be rough. Then you have to profile it, then polish it, means grind it, right? So that your surface will be smooth enough. And then you remove contaminants from the surface by etching it. Then you again polish it, and you inspect whether there are any defects or not, because you don't want any defects in your wafer, right? Then you clean it, then you package it, right? So this is what is means foundries buy, right? So when foundries or fabrication facilities or fabrication houses, they buy wafers. They buy wafers like so in the packaged form, right? Okay. So so basically the doping, right? So when I talk about P-type substrate, so it is easy to dope the crystal, right? Silicon crystal with P-type dopants during the crystal growth technique, right? And you could add impurities, right? So when you are doing the crystal growth, right? When you are melting the silica, right? So that time you could add impurities. So, based on the concentration of the impurities, you define the resistivity of the initial substrate, right? Resistivity of the substrate, right? And this graph you have already shown. The resistivity will depend on the doping. If you have higher doping, so your resistivity will be less, right? Okay. So when you talk about wafer sizes, right? So wafer sizes, so um, in the 1970s, when the CMOS processor started, right? We started with 100 millimeter wafer, right? 100 millimeter is 4 inch, around 4 inch, sorry, 100 millimeter wafer. So so then we move to 6 inch. So this is 4 inch. So this is 6 inch wafer. In 1980s, we moved to 150 millimeter wafer size. So when you talk about 150 millimeter, this is the diameter of the wafer, right? And 90s, we moved to 200 millimeter. Then 2000s, we moved to 300 millimeter. And so we are still continuing with 300 millimeter wafer size. So there are a lot of discussion from last 5 to 6 years to move to 450 millimeter wafer. So so this is 8 inch wafer. This is 12 inch, uh, right? And so so there is a plan to move to 450 millimeter wafer, but I mean, 450 millimeter have not been used yet, right? So maybe in future people will move to the fabs and foundries will move to 450 millimeter wafer size. Right? So when I talk about 450 millimeter wafer size, so you could really imagine how big the wafer is, right? So the wafer is the diameter of the wafer is half a meter, right? So half a meter diameter is really a very big wafer, right? And and here you can see the picture of a 200 millimeter wafer and a 300 millimeter wafer, and you could see the difference, right? So the size is really these wafer sizes are really big, right? Okay, so basically, when I talk about 8 inch, 12 inch, or right, so so 8 inch wafer, the last technology node which used 8 inch wafer is is 130 nanometer, right? So so the 130 nanometer node is the last node which used 8 inch wafer. So when you moved from 130 to 90 nanometer CMOS technology, so in the industry switched from 8 inch wafers to 12 inch wafer, right? And so 12 inch wafer people started using it from 90 nanometer CMOS technology, and many fabs started using it in 65 nanometer, right? So 65 nanometer is the next CMOS node of 90 nanometer. So so many fabs started using it in 65 nanometer CMOS technology node, right? So that means, so all the technologies, all the means, like let's say you are talking about 90 nanometer CMOS technology. So all these 90 on all over the world, right? 90 nanometer CMOS technology use 12-inch wafer size or 300 millimeter wafers, right? And when you're talking about 130 nanometer all over the world, they use 200 millimeter, right? And like 180 nanometer CMOS technology, so also we use 8-inch or 200 millimeter wafers, right? Right? And so like 130 nanometer, 180 nanometer, 250 nanometer, and so they are using 200 millimeter wafer sizes. Then when you go to 350 millimeter technology, 350 nanometer technology, right? So there people, means industries were using 6-inch wafers, right? So what is the means, basically the size of the wafer is driven by something called the fab economics. So basically, so when you take a wafer, right? So when bigger the size of the wafer, you could get more number of dies. So here, see, I don't know whether you understand this thing or not. So, uh, so this is the size of your IC, right? So when you let's say you are tapping out a microprocessor IC, right? So your microprocessor IC will have some width and some length, right? So this is the area, right? So this is the area of one microprocessor IC, right? So right, and so this may be, let's say, 100 millimeter square, right? So typical circuit means, let's say you have designed a circuit which is 100 millimeter square, right? Right. So basically, when you're talking about a 200 millimeter wafer, right? So 200 millimeter wafer. So what is the area of a 200 millimeter wafer? So this is pi by 4 into 200 millimeter square, right? Right. So this is the area. So from this area, how many microprocessors? Let's say this is one IC. So how many ICs you get? So the total area of the wafer divided by the area of your circuit that you have designed, right? So larger the diameter of a wafer, you could get more number of circuits, right? So let's say to fabricate, right? So to fabricate one wafer from starting to end, right? So to fabricate one wafer from starting to end, let's say it incurs around $5,000, right? So $5,000, this is the fabrication cost of the wafer, right? From the wafer starting, that means you take a P substrate, then you fabricate your circuit, then you go to metal and everything, right? So let's say it takes around means the cost of production is $5,000, right? So if you're getting, let's say, 500 ICs from there, that means, so one IC will be $10 cost, right? So this is how the cost of your IC is determined, right? So it also means, basically, let's say you have 500 ICs, then also the cost will depend on how many of that ICs are working. This is the yield of the process. So let's say all ICs are yielding, all ICs are working. So then the cost will be $10, right? But if you have a bigger, right? So if you have a bigger wafer, then so let's say you have again this cost of fabrication is $5,000. Since you will get more number of ICs, let's say you get 2,000 ICs, right, from here, right? So then in that case, your cost will be $2.5, right? So the cost of the IC means is continuously reducing, right? So that's the reason the industry has moved from smaller size wafers to larger size wafers, right, with time. So so this is called the economics, like, so basically we are scaling our the size of your IC is also reducing. Also we are getting more number of ICs from a single wafer. That's the reason the cost of each IC is reducing over time, right? Okay, so this just shows you a chart, right? So when your people started using 200, 300 millimeter wafer in early 2000, right? Early 2000, when 90 nanometer CMOS technology uh, is developed, right? Right. And the 450 nanometer, as I told you, so we are not at, means, using. Industries are still debating whether to go to 450 millimeter wafer size or not. Okay, so this is about the starting material. So the starting material is a wafer, right? So you have, so now what you get is a wafer, right? So so basically your starting material is a wafer, right? So wafer, it can maybe, so if you have 180 nanometer CMOS technology, so this wafer size is 8 inch. If you have a 65 nanometer CMOS technology, that wafer size will be 12 inch, right? So, and that is a P-type wafer with particular resistivity, right? With a particular resistivity, right? Resistivity depends on doping, right? So when you buy a wafer, so you will tell the wafer vendor, okay, I want this much, this number of wafers. Let's say I need 100 wafers with 100 wafers, the P-type wafers with this much resistivity, right? Then they will supply you those wafers. Okay, so then the starting material is a wafer, right? So this is, we call this is the substrate, right? So because we'll build our transistor on top of that wafer, so that's why this material we call the substrate, right? Substrate, right? So the first process is to create, means to create active areas for NMOS and PMOS transistor, right? So in your IC, right, when you are designing an integrated circuit, So you have two kind of transistor, right? You have NMOS or PMOS. You don't have anything else in your circuit, right? You have NMOS transistor or PMOS transistors, right? So, but we have to separate NMOS and PMOS transistors, right? So that's the reason we have to create the active region for the NMOS transistor and the active region of PMOS transistor. And this is done by the trench, right? Shallow trench isolation, right? So you have to create these trenches between NMOS and PMOS transistor to separate it. So, so this is the shallow trench isolation. So basically, so what you have to do, right? So you have to you have to means what you do is, so you take the wafer, then deposit some mask, right? So basically here we deposit oxide and nitride layer, right, on top of that wafer. Then you use the active mask, right? So we have a mask, right? So active mask and use the photolithography process. We'll just slowly, I mean, we'll discuss this photolithography process a little bit. So then you etch, right? So you etch this part, right? So this is the etching process, right? So you etch this, remove this oxide, nitride, and silicon, right? So after you etch, right? So this, as I told you, right? So you have to do photolithography process. So what is photolithography process? Let me quickly uh, tell you, right? So here, let's say you have your substrate, right? Substrate. Um, uh, this is the substrate, and you want to create a trench, right? So basically you have to do the photolithography. So here uh, you have to deposit let's say something called photoresist, right? So this is the masking material, right? So you will mask the whole silicon, right? So you deposit some material on the whole silicon, right? So this is called and this might be, so we have two kind of masking material. We can have soft mask, which is resist, or hard mask, right? I mean, so we'll not go in detail what is soft mask and what is hard mask. And this is typically your resist, and these are the oxide nitrides, right? Right. Okay. So then this is your, then we have a mask, right? So your mask, let's say I want to um, create a hole. So this region will be masked. So mask is nothing but this is a glass, right? So glass, and we have coated chrome in some part, and some part is open, right? Then let's say this is your mask. Then we have your light, right? So light, right? So the light will interact with the resist on some part, right? So this region, this if this is resist, right? So the so when the light falls on the resist is a chemical compound, right? When the light falls on that resist, the properties of the resist changes, right? Then this part can be dissolved, right? So you can develop it, right? So when you develop it, so this part could be removed, right? Could be when you could easily etch this part, right? And other part could not be etched, right? So then, right? So then so okay, so now this part is uncovered, right? Then you could etch the silicon, because this part is this part is covered, but this part is open. So here you could etch the silicon, right? Etch the silicon. This is how photolithography helps, right? So photolithography helps in masking some part and unmasking some other part, so that you could do your processes, right? So this, when you talk about photolithography, the photolithography is not a single process step, right? It is a sequence of process steps, right? So like as I show here, as it is shown here. So so you have a multiple process steps, right? So let's say you have wafer. The first thing you have to do is to coat the wafer with photoresist, right? So to coat the wafer with photoresist, then the bake the resist, then this is your mask, right? So the black one is your mask. Then you align the mask and expose. Expose means you pass light, means you expose it to the light, right? Then so some part of the resist is exposed, some part of the resist is not exposed. Then you have a post exposure bake, right? And then you develop means the portion of the resist which is exposed that could be easily removed, right? So once this portion is removed, then you could do whatever you want to do in that unmasked region, right? So right, so right, so and then you stripe the resist, right? So once you have done your processes, then you could stripe the resist, right? So this is the photolithography process. But when I'm talking about active, right? So in the layout, you have drawn it like this, right? So in the layout, let's say you have drawn, this is my NMOS area, right? Okay. So let's say you have drawn, this is my NMOS area, and you have drawn, this is my PMOS area, right? This is, let's say this is your PMOS area, this is your NMOS area, right? Right? And you have an isolation between, you have separation between NMOS, PMOS. So then let's say this is your wafer. I am drawing a square wafer, right? So if this is my NMOS and this is my PMOS, so this is my active region, right? So this is your mask. This is the layers that you have drawn, right? So this is your active layer that you have drawn, right? This is the active layer you have drawn. So your mask, that means your mask only, this is your masked region. So this portion will not be etched. Other regions will be etched, right? So other regions other than this highlighted regions, other regions will be etched, right? Right. So after processing, after you form the STI, so you will see. So if this is your silicon, so this is your NMOS region, and so this portion will be STI. So this region will be STI, and this region will be shadow trench, right? That means this is your NMOS region, and this is your PMOS, right? Right. So this is right. Okay. So any questions here? Okay, so if not, then go ahead. So this is the cluster of means equipments that you use for a lithography process. You use coat.
Sir, sir, what are the doping concentration for the P-well and the N-well?
No, this is the active definition. I'm not implanting here.
Okay,
So these are all P-type substrate, right? So I'm
okay,
just defining the regions. Huh.
okay, okay.
Okay.
Sir, we are discussing 130 nanometer process. Sir, what does this 130 refer to?
Oh, this is a name, right? It doesn't refer anything. It's just a
It's
name.
not a, it's not referring to any length or something.
No, no. It's just a name.
Okay, sir.
Okay, we will discuss it later. Maybe towards the end of this course, I'll tell you what we mean by different CMOS nodes and all those things. So at this point, you just keep in mind. So when I talk about 130 nanometer, this is just a name. This does not tell you anything about the technology, right? So if you want to know more about the technology, so you have to go to and read the design manual of that technology, right? Our design rule file, right? What is the minimum dimensions we could use in those techniques, all those things. So yeah. So okay. So now, so this is lithography. The lithography cluster, right? So we call it because we have means many tools which do the same thing. So we have a coater, we have a bake, and we have an exposer. So this is the expensive, this is the most expensive tool. That is the exposer tool. And then right then, so basically, if you see, this is a spin coater, right? So your resist is coated using a spin coater, right? Then you pre-bake it. That means you heat it at some temperature. Then you expose, right? You use your mask, then expose. Then you have post exposure bake. Then you develop, right? So then you do your process, right? Okay, so we'll discuss these things when you study the microfabrication, right? So once you etch these trenches, right? Once you etch these trenches are filled with oxide, right? So then you fill oxide. So this is a precursor. We call it tetraethyl orthosilicate. So this is a precursor for silicon dioxide. So basically what you do is just keep in mind. So you have created trenches, right? Then you fill it with oxide, and this is done by the deposition process, right? So you have deposition process. So I'll briefly tell you about what is deposition process later. So then you etch it, right? So basically you have deposited, then you have to polish, right? So basically you etch some portion of oxide, right? So because this portion of oxide you could etch, right? Right. So you etch it, then you remove, right? You remove this. This is the nitride. So you remove this nitride. So then you have your salutens formed, right? So this is your p-type substrate here, right? And this is your Salutrans isolations, right? STIS, right? So the Salutrans isolation just separates different devices, right? So when I talk about different devices, so this here, this region, this island that you're talking about, right? So this island can be used for NMOS transistor. This island can be used for PMOS transistor, right? Also, this island can be used for NMOS transistor, right? You want two NMOS transistor, but you don't want to connect them together, right? So basically, so now the STI just gives you different islands, right? Then you use those islands to fabricate different devices. Okay, so so after this Salutens isolation, so after that you have done. So then you have a oxide thickness, right? So you just grow a thin oxide. When you're talking about grow, so there are two processes. One is growth, right? So you grow oxide or you deposit oxide. So there are two different processes, right? Deposit oxide is not a very good process. So when you want to like feel something, then you deposit, right? But when you want to because silicon dioxide, your get dielectric, everything, you grow oxides, right? So what is the difference between growth and deposition? So growth is nothing but thermal oxidation, right? So thermal oxidation is nothing but like you have a furnace, and then you means the furnace has let's say you put your wafers inside that furnace, then you pass oxide, then you heat that furnace, right? So basically the oxide, when the furnace is heated, so that means wafer is at certain temperature. Then when you pass oxide, or sorry, you pass oxygen, so oxygen reacts with silicon, then forms silicon dioxide. That is the growth process, right? That means growth is your oxygen reacts with silicon surface and forms silicon dioxide, right? That is the growth process, right? Another is deposition. So another deposition, so we call it CVD, right? Chemical vapor deposition. It can be low pressure, high pressure, different pressure CVDs. Right? CVD is your oxide is not oxygen does not react with silicon surface and form oxide. So oxide is formed somewhere else. Then they are deposited on top of the wafer, right? So that is the CVD process, right? So basically in a deposition process, your interface between your silicon and oxide will not be very good. But in growth process, since the oxygen reacts with silicon, the interface will be much better, right? Compared to, so the interface between silicon dioxide and silicon will be much better in oxidation process compared to deposition process, right? So there are different kind of CVD process like plasma enhanced CVD, low pressure CVD, atmospheric pressure CVD. You deposit using CVD process and you grow using furnace oxidation, right? So we call it oxidation. That means it's a growth process, and the deposition is just to deposit oxide, nitride, or whatever you want to deposit. Right? Okay. So then basically you so you have a sacrificial oxide grown on top of the wafer, right? So now you form the N well and P well. So there you have to form the N regions and P regions. That means your NMOS and PMOS, right? So PMOS will have N well, right? So PMOS will have N well and NMOS will have P well, right? So you do that, right? So you have N well, then you will have P well here, right? Right? Okay. Right. So basically, when you form the NOL, you are masking the means when you're forming the NOL, you are masking the P. So basically, when we're putting the N well, you're masking the NMOS part. When you're putting P well, you're masking the PMOS part, right? So and when you're forming N well, so your dopants are phosphorus or arsenic, right? Phosphorus or arsenic. And when we're doing P well, your doping is boron, right? Your doping means your dopant is boron, right? So so boron is a P-type dopant, and phosphorus and arsenics are N-type dopants, right? So this is how you define P well and N well. Then this doping is done through the ion implantation process. So this is the ion implantation process. Basically, if ion implantation process is nothing but uh, you have dopants, right? So you have like gases, right? Let's say bromine or phosphine. Let's say you have PS3, the phosphine gas. The phosphine gas, you ionize the gas. That means you separate the phosphorus. Then you accelerate that phosphorus ions, right? So you accelerate the phosphorus ions, and the implanter what it does is this is mechanism. So you separate phosphorus ions. Then by help of electric field, you accelerate this phosphor ions, right? This phosphorus ions is accelerated, then they're implanted to the wafer, right? Right. So basically, you have a wafer here, right? So or let's say you have your wafer here. So your phosphorus ions are accelerated and implanted, right? But you need ions because ions can be accelerated. If you have a neutral molecule, that cannot be accelerated, right? So ions, like you then you implant, right? So the implantation, how deep you want your phosphorus to go into the wafer, or how much phosphorus, like that is your doping concentration, right? So this is defined by the dose. That means how much phosphorus you want to dope, right? And on another one is the energy. Energy is how deep you want your phosphorus to go, right? So this is defined by the parameters dose and energy, right? And this is the typical implantation process, right? If you want to implant phosphorus, you have phosphorus ions. If you want to implant arsenic, you have arsenic ions. If you want to implant boron, you have boron ions, right? Right? And boron is a P-type dopant, and arsenic, phosphorus are N-type dopants, right? Okay, so
Sir,
this is
doping.
yes,
Sir, these dopings are uniform or on the.
dopants, sir.
Sir, the dopings are on the are uniform in the surface, or it is like
Yeah. So,
A.
so you have a beam, right? You have a beam, right? So basically, if you see, so you have a beam, right? So let's say this is your beam. So a beam of electrons. If you're asking something, so if this is your wafer, so you will have a beam of electrons, beam of ions coming, right? So this is your beam, right? Then you will scan the surface of the wafer with this beam, right? And let's say, but your wafer is masked, right? So let's say you want your boron to be doped in this region, so other regions needs to be masked, right? So एक रीजन मास्क होगा, जहां पे मास्क नहीं होगा, so your phosphorus or boron will go to that part, right? Right? Is it clear for this?
Yes.
Sir,
Okay. Hmm.
sir, if we are already giving ionized dopers, sir, so uh, uh, how will it help in giving me electron? So if I'm giving P plus.
No, right? So basically, the you have silicon, right? So if you have a phosphorus dopant, phosphorus has, so if the silicon is replaced by phosphorus, you will have one electron free, right?
Sir, but I'm already giving ionized phosphorus now, so it has already lost one electron before going into the silicon.
Oh, yeah. So yeah. But when they're implanted, right? So they are phosphorus, right? They're implanted as phosphorus, right? Right. So this basically, yeah. Let's not go to the ion implantation process here, right? So just you just at this moment you just keep in mind that you are implanting phosphorus to the silicon wafer, right?
Yes, sir.
Right. So means this again, this will be a full 1 and 1.5 hours topic, the ion implantation, right? Let's not go to that at this moment.
Yes, sir.
All right. So this is a ion implanter. right? We call the ion implanter. So ion implanter is a single wafer process, right? So it will implant one wafer by wafer, right? Okay. So after we have means NOL POL definition, so we have NOL and we have POL. Now the next step is the gate oxide. So gate oxide, as I told you, right, it will be grown, right? So what we'll do is we'll grow oxide. That means we'll put the wafer in the furnace and heat the furnace and pass oxygen. So oxygen will react with uh, silicon and form silicon dioxide, right? So we'll form the gate oxide. So after the gate oxide, right? So so we'll have gate oxide. Then after the gate oxide, you deposit polysilicon, right? So basically you deposit silicon, right? So when you deposit silicon, right? But silicon is deposited on top of oxide, right? So it will form polysilicon automatically, right? So depending on the temperature of the process, so it will form polysilicon, and the polysilicon grain size will depend on the temperature, means on the temperature, how you're processing, right? So on your process conditions, right? So basically, see why it will be polysilicon, why it will not be single crystalline silicon? Because for the crystal silicon, for crystalline silicon, monocrystalline silicon, so you have to because you need a crystal structure, right? So if you deposit, let's say you have you have silicon and you're depositing silicon on top of it, right? Right. So it will be monocrystalline or monocrystalline silicon, right? Because it will take the crystal structure from the silicon, right? So it will grow on top of silicon, and it will, right? But here I have silicon, and now I also have silicon dioxide, and I am depositing silicon on top of that, right? So this silicon is not getting the crystal structure, right? Because see, I mean, it's not getting the reference, right? So here, uh, when you deposit silicon on top of silicon, it will take automatically the crystal structure from the silicon, right? But here I have silicon dioxide. Silicon dioxide is amorphous material, right? So this silicon will be polycrystalline, right? So when you deposit silicon on top of silicon dioxide, so it will be polycrystalline silicon. Okay. So after this, we know that means we have learned that for NMOS transistor, I need N plus polysilicon, and for PMOS transistor, I need P plus polysilicon, right? So that's why I have to dope these silicon regions, these polysilicon regions. So polysilicon is your gate, right? So you have to dope these polysilicon regions. So then I have to mask, right? So if this is my NMOS, right? So I'll dope this polycrystalline silicon with N-type dopants, and if this is my PMOS, right? So then I'll again mask and dope this region with P-type dopant, right? So then I'll have N plus poly on NMOS transistor and P plus poly on PMOS transistors, right? NMOS and PMOS. So after that, I'll etch the gate, right? So you will etch the gate, right? So you have to then this is again the lithography process. So you have to mask. So this is your mask. This region is masked, right? And your polysilicon will be removed from the unmasked part, right? So if you etch it, then you will have this is your polycrystalline silicon. So this silicon will be left behind, right? So other part is etched, right? So so this is your gate, right? So this is your gate, right? This is how the gate is formed, right? So you have to you deposit polysilicon, then you etch, right? So when you do the layout, right? So when you do the layout, you see you have your gate layer, right? Right? So this is the mask part, right? That means this region is masked, right? So you are drawing this. So when you are doing the layout, you are drawing this region, right? That means this region is masked, right? This is your gate, right? Okay. So so this is a photolithography process here, right? So this is a photolithography process here. So you this is your gate mask, right? So you could see this is your gate mask here, right? Your gate mask here, right? Then you pass light to the mask. That means this region is masked. So if you have photoresist, so some part of the photoresist will be exposed to the light. So So the part which is exposed to the light can be developed, right? That means can be removed, right? So then this photoresist is not exposed, that will stay. Other part which is exposed, that can be removed, right? Then you see you have a photoresist in this one part of on top of polysilicon, and the other part is exposed, so that part could be removed, right? So then you etch, right? Etch this part, so this part will be removed, right? So after you remove the polysilicon, this is how it will look like, right? So this is a TM picture, right? We have taken some um, uh, the means transmission electron microscope, means microscopic image. So this TM image, you could see this is how your gate looks like um, on wafer, right? So you see when you do the gate edge, typically your edge, right? So when you study, right? So you tell, okay, your um, you have your gate is perpendicular, but actually this is not, right? So if you look at the actual devices, right? In actual case, this has a finite slope, right? So these are not actually perpendicular to the silicon. And this is your gate length, right? So here the gate length is around 56 nanometers, right? And also you see this cross section is taken a different part of the wafer. So even if you have drawn the same layer, right, same polysilicon layer, right, you see in one case it is 56 nanometer, other case it is 57. So there is the variation, right? So this is the variation in the gate length that you get across the wafer, right? Okay, so this is my gate, right? So then you form a offset spacer. That offset spacer is you just deposit a thin layer of oxide. This is again deposition process. This is not grown. So you deposit a thin layer of oxide. So once you drawn it, means grow a thin layer of oxide. So this part is your oxide. You can see this oxide is grown. I mean, it's not grown. This is deposited. So you deposit a thin layer of oxide. So now you will form the extension, right? So then you will form the extension part, right? So extension करने के लिए, so if this is your NMOS region, so NMOS extension will be N type, right? And PMOS extension will be P type, right? So so what you do, you have NMOS, your NMOS part is exposed, right? So you see your let's say this is PMOS region. So your PMOS region is masked, right? I'll go here, right? So your PMOS region is masked, right? PMOS region, here you see PMOS region is masked, and NMOS you are implanting arsenic, right? So arsenic is being N-type dopant, so it will create this extension, right? And please see, this is a self-aligned process, right? So I will write this is a self-aligned process. Self-aligned process, that means uh, so your source and drain, your extension in this case, right, your extension is aligned to the gate edges, right? So your extension is aligned to the gate edges, right? So your extension will only be implanted in the area where there is no gate, right? And this is a self-aligned process. You are not, I mean, it is done automatically, right? So this is self-aligned process. So similarly, you will implant arsenic. So this will create an extension, and you'll do BF2 or boron. This is boron. So let's think this is boron, right? You'll do boron to have P-type extension, right? So you'll have P-type extension, right? Right. So you have N-type extension now, and you have P-type extension. So after that, you have to form the N source drain, right? So in 130 nanometer process, so 130 nanometer process has, I mean, it's a typical structure, right? So it has actually two steps, right? So you have extension, right? Then you have, so they means basically just to control the short channel effects. So they have a two-step process, right? So you have extension here, right? This is your extension, right? Then your first source drain, then your second source drain, right? This is your first source drain, and this is your second source drain. So it's not necessary to do it in this way because, but many foundries have done it in this way, right? So you have a extension, then you have a first source drain, then you have a second source drain, right? But once you have done the extension, then then you have to implant, right? So this extension and source drain implants are self-aligned processes, right? So to make it self-aligned, then you have to deposit some dielectric in this region, right? So some dielectric region, right? And that dielectric is called spacer, right? So so this is dielectric is nothing but your nitride, right? So you deposit nitride, right? Then etch nitride, right? You deposit nitride and etch nitride, and you don't need any mask here, right? You deposit nitride and you do etching. So when you do etching, so some of the nitride will be left here, right? And this is called the this is your spacer, right? This is your spacer. Then when you implant, right? Now when you implant on top of it, right? Then again it will be a self-aligned process, right? Because your gate, then gate का side में दो spacer आ गया, nitride spacer. Then when you implant, then this region will be automatically masked, right? This region will be automatically masked, right? Right. So then so similarly you create the first source then. So for the PMOS case, you do boron implant, and for NMOS case you do arsenic implant, and you have this first. These are the first source then, right? So you follow the same process, right? You create another spacer, right? You again deposit nitride and etch it. So you create another spacer. So this is the first spacer and second spacer. So you see, so this is your first spacer, right? And this is your second second spacer, right? Right. So now you again, so if you take a cross section, and this is you could also see the cross section here. This is your gate, right? This region is your gate, right? So this part is your first spacer. This is your first spacer, and again you have a second spacer, right? You have a second spacer. This region, right? So so you create these spacers. Then you have created the second spacer. Now, if you do this boron and arsenic implant, so then you will create the second source then, right? So you have created the second source then, right? So this is your second source then, right? So these two are second source then. So, but it is not necessary, right? In typical processes, so this is one of the process where you have two source drains, right? First source drain and second source drain. But in 180 nanometer CMOS technology, you have only one source drain, one extension and one source drain, right? So in 180 nanometer, you have your gate, right? And you have one source drain and you have a second source drain, right? Right? So, right? Okay. Uh, but uh, but this is a standard, right? So and we have only one spacer, right? So you have one spacer here, right? One spacer, right? You have only one spacer. Right. But if you want to you want a very good device, you want to control your short channel effects very well, then you can have also two-step process, right? You can have two source drains and one extension. Right? Then for that you need some extra process steps. That means you need one extra spacer. Okay, so okay, so it's already more than 12. Uh, uh, so anybody has classes now? Nobody? Okay.
Sir, I have a lab after that.
Okay, so just give me 2 or 3 minutes, I'll finish, right? So once you have done the source and drain, then you silicide this part, right? So then basically, basically you deposit cobalt. So this is cobalt. So this is just done to reduce the source drain resistance, right? So you just deposit cobalt and you anneal it, right? So when you deposit cobalt and heat it, right, then the silicon will react with cobalt and form cobalt silicide, right? So this region will be silicided, your source drain and your gate will be silicided, right? So this ends your front end of line process, right? So, so from the beginning till silicidation, right? Silicide, right? This is called the front end of line process, right? So, so please keep in mind when you implant, right? So I have already told you, right? When you implant, right? So implantation only will not dope your things. So you have to implant, then you anneal it, right? Because you see, let's say, I mean, you have silicon, right? So you have silicon crystal, right? Silicon is arranged, right? And you are implanting phosphorus, and phosphorus will come to the interstitial, right? When you implant it, right? But to activate, right? So what you have to do is you have to replace this silicon. You have to replace this silicon by arsenic, right? So that is done once you implant it. Arsenic is implanted to the silicon, but I want arsenic in the active site. That means arsenic should replace silicon, right, in the crystal, right? So that is done by heating, right? And that process is called annealing, right? So always this implant process step follows followed by annealing, right? So you implant, then you anneal, so that your dopant is activated, right? So you implant your arsenic, but arsenic has to go to the silicon site, so that has to replace silicon. So that is done by the annealing, right? So when you talk about dopant, right? So we discussed, right? So we have around 10 to the 22 silicons per centimeter cube, right? So that is the density of silicon, right? Um, right. So, but we have to, when I'm talking about dopants, that means we are replacing some of the silicon by the dopants atoms, right? So when you're doing arsenic implant, or we forming n-type, so when you're doing n-type dopant, so we are replacing this silicon with arsenic. When we p-type implant, we are replacing silicon with boron. That means, let's say I have 10 to 22 silicons per centimeter cube. So, and if I'm doping 10 to 20, that means I have removing 10 to 20, I'm replacing this 10 to 20 silicons by arsenic, or replacing this 10 to 20 silicon by boron, right? So this is called implantation process, right? So doping is nothing but you are replacing silicon by another material. In that case, we have arsenic or phosphorus or boron, right? If arsenic, phosphorus, then it is n-type dopant. That means you are replacing silicon by n-type dopant, so the metal will become n-type. And if I'm replacing silicon by a p-type dopant, so the metal will become p-type. Okay, so we'll stop here today, and I think I thought I'll finish the process flow, but I could not do it. So anyway, so we'll continue our discussion tomorrow.